Hi, we are back with our discussion of the RSA crypto system. So what we're going to do in this video is we are going to ensure that the encryption and decryption functions are inverses, and I'm going to also lead you to what is going to come for the rest of the semester. So we'll see a little bit of stuff about computational complexity in this video, and then I'm going to leave you with a list of things that the next videos will cover. So let us just recall what the RSA crypto system looks like and what the various letters are standing for. So we have a number n, which is p times q. P and q are prime. We have a number selected b such that a and b, well, we have two numbers, I guess, a and b, that are congruent to 1 mod phi of n. And then with these numbers, n, p, q, a, and b, we have an encryption function that looks like this. ek of x equals x to the b mod n, and dk of y equals, so this here is y, dk of y equals y to the a mod n. So after our previous lecture, you will have designed your own RSA crypto system, and you should have checked that once you encrypted something, that if you took your encrypted text and then used the decryption function, you got back to what you started with. So we're just going to make sure that that happens in general. We're going to verify that these two functions indeed, ek of x and dky of y, are in fact inverses of one another. Okay, so let us start with this statement here, that the a and the b that we've chosen for our exponents in our encryption and decryption functions are indeed they are indeed inverses. We chose them that way. So that means that there are two numbers s and t, so that sa plus tb is equal to 1 mod phi of n. Okay, that's we could find those s and t with the extended Euclidean algorithm. Okay, so we're going to start down here. We're going to say AB congruent to 1 mod phi of n. That means that AB is equal to t times phi of n plus 1. Okay, if two numbers are congruent to 1, then it must be the case that that number AB can be written as a integer multiple of the modulus plus 1. Okay, so here t is greater than or equal to 1. Okay, next thing I'm going to say let x, so this is the plain text that we're going to encrypt, let x be chosen from the set Zn star, and by that notation I mean Zn star means the invertible elements mod n. Careful note of that. Zn star means the invertible elements mod n. Okay, so we are now going to take our encrypted x, that looks like this, x to the b, that's y, and then we are going to apply the decryption algorithm to it. And what we want to show is that when I do that, I get back x, because that means that the two functions are inverses, and my decryption function will undo my encryption function. Okay, so what does this look like? This looks like this, x to the BA, which is x to the AB. And AB is this guy right here. AB is t times phi of n plus 1 mod n. Okay, and that is congruent to x to the phi of n to the t times x mod n. Okay, so that is just using the exponent laws here, going from here to here. And then what is x to the phi of n? Let's think about that. What is x to the phi of n? That, in fact, is 1. Why? Because that is a corollary of Lagrange's theorem. So let us just make a note of that. That is the corollary of Lagrange. And that is if B is an invertible element in Zn, then B to the phi n is congruent to 1 mod n. So I started with the assumption that the thing I'm going to encrypt is indeed an invertible element in Zn. So therefore, when I raise it to the phi of n, I get 1. So that is 1 to the t times x mod n, and that is equal to x mod n. Perfect. I mean, that is exactly what I wanted to show. That is that x to the b, I encrypt x by taking x to the b, then I decrypt it by raising it to the 8th power, and I get back what I started with, my plain text. So that is for when x is in Zn star. Now, consider when x is in Zn, remove Zn star. So x is not an invertible element mod n. So that means that this is where the problem is going to be. This is not necessarily equal to 1. So that is something to consider. So I have gone through this and I have done it for the invertible elements. Now I want to consider x to be not invertible in Zn, because the plain text really could be any x in Zn. So what I'm going to do is ask for you guys to try this out. Try this out, and this is what we'll cover during the lecture on, hopefully on Wednesday if we have time. If not, then next week. So try this out. Try this out. See if you can adapt the argument above so that we can have it for all x in Zn. I want to just say a few things here tangentially related to what we're talking about here. I just want to remind you of Fermat's little theorem, and that is a to the p is congruent to a mod p when p is prime. And that actually can be used to attempt to find prime numbers. So we are going to come soon to trying to understand how we're going to get large prime numbers. Not much use having a crypto system that's based on the security of multiplying together two large prime numbers if you can't find those large prime numbers. So we're going to do a little bit of work about understanding how to come about finding large prime numbers. And one method actually is there. So this is something that we could, some methods of doing that. There is, using this Fermat's little theorem, we could have the Fermat primality test. That is one option. What we're going to see, there is a algorithm called the Miller-Rabin algorithm for finding large prime numbers. And then I'm just drawing your attention now for as a preview of what's coming. There is the Solovay-Strassen algorithm, and that is the one we are going to focus on. So we will be using this to take a number and then determine as best we can. You'll see it's actually not deterministic, it's a probabilistic algorithm. We'll be using that to determine whether some given number is prime or not. So like I just said, that's going to be a probabilistic method. There is in fact actually a deterministic polynomial time algorithm for determining whether a number is prime, and this is not something we're going to cover at all. I merely bring this up for your interest, that you may want to look it up. It's very recent. This is the AKS algorithm. It's from 2002, so this is a recent breakthrough. It's general. It's a polynomial algorithm. It's deterministic, so it answers yes or no, and it's 100% correct. Deterministic. So that is something unfortunately we won't have time to cover. So we are going to focus on this one coming soon. Okay, so that's something that's coming. So this sort of leading me to the things we want to talk about, aspects of RSA that we still need to discuss. So let me just make a list of those things here, and then I'll do one thing here, and then I'm going to make a series of shorter videos going forward, each about one of these aspects. So aspects of RSA to discuss. Sort of the setting it up details in setting it up. Okay, that's going to include finding the large prime numbers. We will also need to talk about the efficiency. I don't know if you noticed when you did your example and you try to do something like this, 4872 to the 400 and who knows, I'm just making these numbers up, like this, mod something or other, like that. How do you possibly do that calculation efficiently? Because if that takes too long to do, that is also not so good. So we're going to be looking at the efficiency, not the possibility of doing it, but the efficiency of encrypting and decrypting. That's going to be an important piece of information. As time permits, as we're going, of course we'll be going until the end of April, so we'll just keep making as much headway as we can. So if time permits, we will talk about some of the security issues. Okay, so I'll just say here is, the thing is not secure. So the one way to attack the RSA crypto system is to factor n. Then you're done. Then that's it's broken. So the ability to mount a successful attack on the RSA crypto system is equivalent to factoring a number n. So we don't know that if there's a polynomial time algorithm for either problem, but should there be one for breaking RSA, then that will imply that there's one for factoring. There is a continued fractions attack on RSA. If we have time, we will take a look at that. So there's a possibility of re-seeing the continued fractions, which, as you may have guessed, I really like. Okay, so let us just note the RSA parameter generation sort of in an algorithmic format here. So we're thinking of making an RSA crypto system. We need to generate all the numbers we need to do this. Okay, so step one is generate two large primes. I don't know actually what the current RSA standard, how large those prime numbers need to be, but they are somewhere in the order of 150 digits long. So they're really big numbers, two large primes. And that will be P not equal to Q. Then you compute N, and I'll put it in sort of computer science way of writing it. N will be populated by P times Q, and then you can easily compute phi of N as P minus 1 times q minus 1. So these are the steps you need to do in setting up your RSA crypto system. Then you need to choose random p. Let's try that again. Let's choose a random b where 1 less than b less than phi of n, and you want it such that the GCD of b and phi of n is equal to 1. So one way is just to get this condition met is to just randomly choose a b and then compute the GCD. If it's not 1, toss that one out and randomly choose another one. Keep going until you get one that is relatively prime to phi of n. Then step 4, compute a as the inverse of b mod phi of n. And then you're done. You are ready to publicize your key, your public key. So you publicize your public key, which is going to be n and b, and then you have a private key, which you don't tell anybody, and that private key is p, q, and a. Okay, so the key is in 2 pieces, one of which is published and one of which is not. Okay, so now that we have the RSA crypto system spelled out, we've done an example, we see how it works, we've assured ourselves that the encryption and decryption functions are inverses. We now recognize that there's a bunch of details that we need to look at in order to actually practically be able to have this system up and running. So the first thing we're going to do is look at the computation time for doing exponentiation. So that is an issue that we need to see an efficient algorithm for. So the first thing we're going to do is look at how long it takes to do it in the most sort of what I will call the grade school way, just sort of the obvious brute force method, and then we'll look in the next lecture about how to do it efficiently. So our first thing to consider in the practicality aspects of RSA is the computation time for exponentiation. Modulo n large. I mean, we're thinking, you are not going to obviously see this in any of our handwritten examples, but we are thinking of n is large. N is the product of 200 or 200 digit long prime numbers. So n is very, very large. So let's just first get a sense of how the computation time for a variety of operations, what it looks like. So this is something I know that particularly appeals to Jeffrey, and he in fact is going to give us a talk shortly on the different computational times of a variety of sorting algorithms. So I'm looking forward to hearing what he has to say about this. This is the same kind of idea, what I'm talking about here, computation time for exponentiation. In order to get at that, we're going to look at some computation times for some shorter operations. Okay, so let x and y be positive integers. Okay, let k and l be the number of bits in their binary representation. Okay, so I'm just going to give an example here so that we see what's going on, and then I'm going to ask you actually, after you see this example, to stop the video, see if you can figure out how to calculate k and l from x and y, and make a stab at it, and then start the video again and see if you agree with what I'm doing. So here's an example. For example, imagine x to be equal to 8. Then the binary representation So that is the binary representation is 1, 0, 0, 0. That's in base 2. So in this case, x is 8 and k is equal to 4. Okay. So, and then if I had another number like this, x is equal to 10, then x would be equal to 1, 0, 1, 0 base 2, and k would still be equal to 4. However, you can see what's going to happen is if x goes to, say, 16, then I will have 1, 0, 0, 0, 0 base 2, and k would then be 5. So I'm wondering, how do I calculate that value k, given that I know the value of x? Okay, stop the video, see if you can figure that out, and then turn it back on and see. All right, so I am saying that how I calculate k, how you should calculate k, is looks like this. It is log to the base 2 of x plus 1. So we see here that the log, these brackets that are just open on the bottom means floor. So that means if you have a number like 2.63, the floor is 2. You have a number like 7.92, the floor is 7. It's the lowest, it's the integer immediately before the number. Okay, so in this case, you can see what's happening is when you take log to the base 2 of 8, you get 3. And 3 plus 1 is 4. When you take log to the base 2 of 10, you get 2 point something. You get 3 point something. I don't have my calculator going here, but it's going to be 3 point something. I'll just put it like this: 3 point something. There's going to be some decimals there. It won't be 4 though, because log to the base 2 of 16 is 4. Okay, so it'll be 3 point something, and then you take the floor, which will be 3, and then you add 1 and you get 4, and that's indeed how long this is. And then, but when you get to the next one, next power of 2 up, you're going to log to the base 2 of 16, that's 4, and then you get 4 plus 1, and you get the 5 digits. Okay, so that's how this is working. And then let's take a look here. L, that's going to be the number of bits in y, and that's going to be log to the base 2 of y plus 1. Okay, so the floor. Okay, so take a look now at how some of what I'm going to call the grade school algorithms work. Grade school. How long does it take? How many operations does it take? So I'm talking about here the grade school algorithms. Okay, so if you wish to add, we're going to do one other thing here. We're going to just assume right here, assume k is bigger than L. It doesn't matter which one is bigger, but we're going to the amount of operations is going to depend on which number is bigger, k, x or y, which one has more bits in their binary representation. But I mean, it doesn't matter which one you choose. So we're just going to, for the sake of simplicity here, choose that k is bigger than L. Okay. So if you are going to add two numbers, x plus y, that will take you big O of k. So this means that the growth rate of how long it takes you to compute x plus y grows as the number of bits in the binary representation of the largest of those two numbers. In this case, that would be x. So it takes 3 operations to add, say, 3 plus 2, and then it takes 4 operations. So I'm thinking here now, what if x was equal to 3 and y was equal to 2? Then that would be, and I'm thinking here of 3 plus 2, then, oh, sorry, I'm going to try that again. I want this, I don't want it to be like this. I want this to be 8 and this to be 4. Then k will be equal to 4 and L will be equal to 3. and then I'm saying that it takes to add this up. I'm saying it takes big O of 4 operations to do that. Okay. And it's important to note that this thing here is linear in K. So as the number just keeps getting bigger and bigger and bigger, it's just taking it. So if it takes 4 operations when K is 4, when K is 15, it takes 15 operations. So this is a linear growth. This is actually quite nice when you see an algorithm with linear growth as the numbers gets bigger. That's usually a fairly nice feature. You want to get these growth rates as sort of low as possible. Like you do not want to see, you do not ever want to see something that looks like this. Okay, that is exponential growth, which means as soon as K gets anywhere even modestly big, your whole system just bogs down because the amount of operations that have to be done are way too large. So the idea is to have polynomial growth. So we want to have that something that looks polynomial growth, which would be something like K to the something. Let us just call it, I don't know, let's just pick a number here, K to the Z. And we want to have Z small as possible. That's the idea. So it means that maybe as your K gets bigger, the number of operation goes up as some power of K, maybe K squared, like if Z was 2, or K cubed if Z was 3, but it doesn't go exponential. And then of course, the smaller that you can make Z, the better it is, the better your algorithm performs as it scales up. So I'm just going to give you some indication of, if you use the grade school algorithms, how long it takes to do a variety of operations. To do subtraction is also that. If to do multiplication, that is K times L. Okay. To do division, that is O of L times K minus L. Okay. So sometimes you'll see this with a weaker bound of K times L. To do the GCD of X and Y, that is going to be O of K cubed. Okay, so this is not linear, it's a cubic, and this is that is here using the Euclidean algorithm. If you find this stuff particularly interesting, I know that Jeffrey does, and it's an important topic in computing science, most certainly, and that is the growth rate of algorithms and analyzing algorithms for their efficiency. And so what you could do now is, you know what the Euclidean algorithm is, and you know how it works to find the GCD. So what you could do is go through the Euclidean algorithm, counting up all of the operations, and see whether you can understand why the growth rate is of order K cubed. So I'm going to say what you're looking then is that the number of iterations is big O of K, and each iteration has a long division, which is of order K squared. So when you combine that, you get O of K cubed. Okay. So if somebody gives you an algorithm, you can easily go through computing all of the operations that need to be done, and then you know for each, anytime you do an addition or a division, that you get this number of this number of operations. Okay, so what are we more interested in? Well, this one we're definitely interested in, and we are also interested in the modular arithmetic. Okay, and in particular, I'm wanting to know, what does it look like to do modular exponentiation, because it's actually the grade school method of doing it is too slow, and we have to look at a much smarter way of doing it, which is what we're going to do in the next lecture. So imagine n is k bits, Okay, and we have two other numbers, m1 and m2, and they're less than or equal to, they're positive and less than or equal to n minus 1. And then we have some other number c, which is a positive integer. Okay, so we can then ask what is the cost of adding these two numbers, m1 and m2 mod n? And that is still of order k, because really what we're doing is we're doing the corresponding integer operation that we just saw up here. We're adding two numbers together, and then we do one single reduction mod m. So that's just that is sort of an insignificant portion. We would not generally write something like this, OK plus 1. We wouldn't do that, because this thing is the dominating term, and that's all. So we have the, so I'm just going to make a note of that, so we understand how come we don't see any difference, and that is because what we're doing here is the corresponding integer operation plus a single reduction mod n. Okay, so similarly then we have m1 minus m2 mod n will also be big O of k. M1 times m2 mod n will be O of k squared. The inverse of m1 mod n is big O of k cubed, and that is via the extended Euclidean algorithm, and also, of course, provided it exists. Okay, so we saw that the getting the GCD was of order k cubed, so it's not surprising that the modular inverse is also OK cubed, because we pretty much get that for free if we keep track of the numbers as we're going through the Euclidean algorithm. Okay, m1 to the c, exponentiation mod n. That is of order log c times k squared. Okay, x to the c mod n can be done using c to the minus 1 modular multiplications. Whoops, modular multiplications. And that is inefficient if c is large. Okay, because this is here O of k squared times c minus 1. There. That is, if you're just going to do it, if you are going to do it with the idea of just looking at x to the c as x times x times x times x times x, and do that c minus times. Okay. In regards to the RSA algorithm, if we're looking at the exponent in the RSA algorithm, c, so this is a little RSA sub note, c, the exponents that we're using can be as big as phi to the n minus 1. Okay, our exponents can be that large, which is almost as big as n. That is actually almost as big as n and exponentially large compared to k. Recall that n is a k-bit integer. Okay, so I am not spending a lot of time on this. What I wanted to just do here is I wanted to go through and just give you a presentation of how long it's taking to do these things, how many operations it's taking, and then that's setting the stage for the next lecture where we're going to learn about the square and multiply algorithm, because that reduces the time to compute x to the c mod n by a significant margin, and that's what we need, because otherwise this calculation in the RSA algorithm, this calculation rate here, well we have both of them. We have x to the b, we have y equals x to the b, and then that's for encryption, and then afterwards for decryption we have x equals y to the a. Okay, those computations have to be feasible to do in some reasonable amount of time. So we're going to look at how to do those calculations with a different type of algorithm so that they are efficiently done. Thank you very much.